Okay, thank you. So I'm actually already down the road in my office at Boston University, where I'll be starting a faculty position. And I'm really excited to tell you about the relationship between Pantheon plus Type Ia supernovae, which we've heard so much about already, and how it's used in the SHOES analysis. But I'll also be talking more generally about Type Ia supernovae. So we've seen the plot on the left, the distance ladder a couple of times today. But what I really want to highlight in this talk is that the Type Ia supernovae in this analysis, in the second and third rungs of the distance ladder, come from Pantheon plus, where you can see our Hubble diagram here at the right. And so I'm going to be talking about the details of why it is so important that both rungs come from the same sample or compilation. And that compilation is 1,701 light curves of 1,550 unique spectroscopically confirmed Type Ia supernovae, ranging from essentially redshift 0 out to redshift 2.3. These samples have been recalibrated. That's 18 different surveys, 25 different photometric systems, and 105 different filters. Having 1,701 light curves of 1,550 unique supernovae means that we have multiple light curves of the same supernova, which comes in handy with studying calibration errors. And we've really made improvements at each step in the analysis, which I'll be highlighting shortly. But what this really means is that we've dug into the last 30 or 40 years of supernova data and supernova samples that have been collected, and collected the highest quality samples that we could, recalibrated them, and by putting them all into the same compilation, we now have doubled the number of supernova calibrators in the second rung of the distance ladder. So we're now at 42, as Adam and others have said, which we believe is essentially complete over the last 30 years out to redshift 0.01. This means that we have an average of 2 photometric systems for each supernova that is in a Cepheid host. So that's 77 light curves of the 42 supernovae, which is important for mitigating calibration uncertainties, which I'll be talking about, and sample selection uncertainties. And so we really pushed on every step of the analysis, where that's sort of depicted here. And I'm not going to go in detail each step, but you can sort of start at this diagram at the top left corner, and we'll work our way around, where in order to actually put the supernovae on the Hubble diagram, which is really the name of the game in supernova cosmology, we first need to model the supernova and host galaxy demographics. We need to model the survey strategy, selection functions, weather, cadence, anything you can think of, we're modeling it. We need to get the redshifts and the peculiar velocities. We need to cross-calibrate the different instruments I'll be talking about. We do photometry. We do this forward modeling photometry, where we model the supernova and the host galaxy that it lives in a forward model. And then we can make the light curves and fit the light curve model and put them on the Hubble diagram, where in order to assess systematic uncertainties, we'll put in perturbations to every step of the analysis, every choice that was made as far as we're able to identify, and propagate those changes, those choices, those uncertainties through the whole pipeline to the end and produce a covariance matrix. And so this is what our Hubble diagram looks like from redshift 0.001 out to redshift 2.3, where I'll note that the SHOES sample is really just the subset of Pantheon plus in this region here. It covers 5 orders of magnitude and 11 billion years of cosmic history. And with this data set, we've really made a state-of-the-art measurement of the dark energy equation of state and omega matter. And we've really pushed on the error floor. We are now incorporating 115 different sources of systematic uncertainty. And thankfully, we are not yet dominated by systematics. Our figure of merit is twice as good as the Pantheon analysis that preceded Pantheon Plus from 2018. We find our constraints are consistent with a cosmological constant. Our main analysis contour is this teal contour here. And when we combine with Planck, specifically the Pantheon plus uncalibrated supernovae, we combine with the Planck constraints and get a very good constraint of the equation of state and of omega matter, which is, again, very much so consistent with -1. The data and likelihoods are available publicly and already being widely used. And even when it comes to constraining evolving dark energy, we are able to make a constraint. While it's not exceptionally precise, it is one of the best constraints of evolving dark energy. It's consistent with 0 from the supernova alone and within 2 sigma when combined with other probes. And so really, there's been a lot of effort to measure. Oh, sorry, I think somebody's unmuted, just so you know. There's been a lot of effort to measure the equation of state, the H of Z expansion history of the universe, over extremely large range in redshift. And really, when it comes to making those measurements, the goal is to understand changes in distance at about 0.02 mag, or roughly the 2% level, over a really large range in redshift, like a delta Z of 2. And so really this, from the supernova cosmologist perspective, is what we're after. And sort of measuring H0 is a really nice byproduct of building our data set so robustly. And from the perspective of a supernova cosmologist, the H0 tension is just really, really whopping. So in order to move H0 at the level you would need to solve the tension, you really need to move about 0.2 mag over a much shorter range in redshift, keeping in mind this is all log space here. So this is a very small range in redshift where things have a very little amount of time to evolve. And so this is relatively what we would consider easy measurement to make from the supernova perspective. And so what we're doing is we're plucking supernovae from the Pantheon plus Hubble diagram and putting them into the full simultaneous distance ladder treatment, where in the second rung, it's just the Pantheon plus magnitudes that are used. They all come from the same sample, but just the magnitudes are used in the second rung, where the distances come from the Cepheids, and you can calibrate the absolute magnitude of the Type Ia supernova in that rung. And then in the third rung, that's when we use the redshifts of the supernova host galaxies out in the Hubble flow, after we've cut out the very local universe and cutting out any departure from sort of the linear regime of the Hubble diagram at higher redshift. And we get the constraint of H0. Now, it's important to note that one of the key benefits of this is that all of the supernovae in both rungs are analyzed simultaneously. They're in the Pantheon plus analysis. They use the same pipelines. They are cross-calibrated. They have systematic uncertainties propagated in the same way, and covariance across the rungs is accounted for simultaneously with the measurement of the Hubble constant. So what we essentially have now is a distance ladder covariance matrix across the rungs, where any differences between the rungs is characterized. Well, first of all, it's mitigated. So we mitigate the differences, as we've heard about a little bit already. For example, we select late type hosts for both the second and third rungs of the distance ladder. We select similar color supernovae and so on. And then any differences that are outstanding, or any systematics that would propagate differently across the rungs, is encompassed in the covariance matrix and accounted for in the systematic uncertainty. So if you really want to test the impact of a systematic, you really need to do this whole self-consistent analysis of Pantheon plus, propagate your systematics across the rungs. You can't just change one of the rungs and then hope that it moves H0. You have to do the whole thing at once. And so you've seen this. It's the 5 sigma chains from shoes, the main result, the one that's what we'd call like the most systematically robust, where the sample has been trimmed down. But what Pantheon Plus has done is we've taken the full sample. We've taken the sample that goes all the way out to redshift 2.3, and we look at extensions to Lambda CDM, like, for example, evolving dark energy, and we can constrain now evolving dark energy with the same data set and the same combined likelihood that constrains H0, and we get the teal contour. when we combine with the shoes data. Now, you might naively think that if we just open up to this parameterization in Planck, you can get a higher value for H naught. But what we find is when we combine the Pantheon plus supernovae with Planck, that is the uncalibrated Pantheon plus supernovae, so we can, statistically do this, because they are consistent with each other when not calibrated, we get the dark blue contour. And so what this shows us is that really it's the Type Ia supernovae that constrain down the H of Z relation at late times that really doesn't allow for evolution of dark energy or things like decaying dark matter, or really any late time solutions to cosmology are just really difficult at this point, as far as we can tell. Okay, so I would like to speak to a couple of questions that have come up ourselves and in the community about the robustness of the supernovae's role in the distance ladder. Okay, so the first question that comes up is it calibration? And I just want to remind people of what we've done on the calibration side, which is to calibrate the 18 different surveys and 105 different filters using the Pan-STARRS all-sky catalog, which covers enough of the sky to overlap with all of the surveys that are used in our analysis, and for which Pan-STARRS is extremely well uniform across the sky. And we allow for a simultaneous recalibration of all of the surveys in the analysis, keeping in mind that we weight the more well-calibrated surveys higher due to their own proprietary calibrations, but we do a refit of everything with conservative systematic uncertainties. And what we find is that we can retrain the supernova model, which is an important piece of this analysis. The supernova model actually relies on the calibration of the samples that go into it. And then we have a covariance matrix, which we propagate to cosmology. And this covariance matrix encompasses the covariance in the calibration across all of the filters, where it's important to note that a lot of the supernovae in the second rung of the distance ladder are coming from the older samples. That is because the second rung is that rate limiting step where we are predominantly have older samples in that second rung. We're continuously updating it, but the point being that you want to account for any possible covariance between older survey filter calibration and newer ones that could be different across the rungs. And so we're accounting for that. Now, with Sasha Brownsberger, we wrote a paper really asking the sort of worst case scenario, which is what if any survey had some residual calibration error that we had not accounted for, that we had not foreseen? How would that affect the shoes analysis or the Pantheon plus analysis? And so you can see constraints of W and H naught. If what we did was allowed an extra free parameter for the calibration of every single survey using the analysis. And what we find is because we have so many different surveys in the analysis that are similar in both the second and third rungs of the distance ladder, and that overlap each other in the Hubble flow regime, any one survey or multiple surveys being off in calibration actually will just essentially self-cancel out. And so you get this really robust measurement. And this is a testament to how the distance ladder works, but also how we've implemented it in the sense that we have so many different surveys that have been compiled and cross-calibrated. Where I'll note that if you don't do the methodology that we've done, if you just use one survey in the Hubble flow, like for example, if you just use the CSP sample, you are much, much more sensitive to the calibration of CSP. And so we essentially are mitigating this possible source of systematic uncertainty. And if you just use CSP, you would get a different H naught that is about 1 kilometer per second per megaparsec lower than what we find using all the samples, keeping in mind that no matter what you do, you have to use a lot of different samples in the second rung because that's how you collect the statistics in the second rung. So really, it would make sense to me to use a bunch of samples in the third rung and to mitigate this systematic. Okay, another question is it the redshifts? We've done a deep dive on redshifts. We've reassessed the redshifts, the CMB corrections, the host galaxy assignments, and we've done a deep dive on a comparison of multiple different peculiar velocity maps. That's what's being shown here, the peculiar velocity modeling codes. And what you find is that there's roughly a scatter of about 0.2 kilometers per second per megaparsec, or even less than that, between all the different maps that you might apply to the supernova data set. Keeping in mind, we've really cut out a lot of the nearby universe, so this isn't terribly sensitive, but you do need to apply some maps. And the reason for that is that the supernovae in the third rung of the distance ladder are not uniformly distributed across the sky by the nature of how the samples were collected. So you need to apply peculiar velocity corrections at some level. And if you don't, that's again another 0.5 kilometer per second per megaparsec, or 0.6. So don't apply any peculiar velocity corrections. Okay, is it dust? So we've done a deep dive on dust, and really, this question is tied in with the question about the quote unquote mass step. And frankly, I wasn't even going to go into this, but there's been some discussion today already about it, so I added this slide, where the mass step is this residual correlation between the supernova standardized luminosity and the mass of the host galaxy that it lives in. And what we find here in Pantheon Plus is that the mass step, the difference between the blue and the red, low and high mass, is really color dependent. And the mass step is really only for the reddest supernovae, which is really the smoking gun of dust. And so we've created a dust model where I'll note that you need a lot of statistics to constrain the dust model. And this is what we do on a population level. We have an intrinsic color distribution, a dust reddening distribution that we constrain as a function of mass. And then the convolution of those produces the data set that we observe. So this is not on a individual supernova basis, but at a sort of a hierarchical level. And what we essentially are modeling is the host mass dependence of the dust properties, and then we can correct for that possibility. And so we've done this in Pantheon Plus, and what I'll note is that a couple of papers are coming out soon that sort of corroborate what we find: a Kolde-Meldorf paper and a Brody-Popovic paper on independent data sets in dark energy survey, SDSS, and Pan-STARRS photometric samples that obtain very similar dust populations and intrinsic supernova populations. But also, I'll point out a key piece of independent work by the Bayes SN team, which is led by Sohail Dewan and Casey Mendel, where they took additional data for a subset of the Pantheon Plus sample, where they have near-infrared information about the supernova light curves, and this gives them an estimate for the extinction or the attenuation of the light curve for every single supernova. And the key thing is that we've done this for both the calibrator sample and the Hubble flow sample. They made estimates in the same self-consistent way. They've redone the analysis, and they find that actually this increases the value of H0. Now, we've seen some talk about it today. I'll show another plot in a minute, but there's additional questions about, well, is mass really the best tracer of the dependence between supernova and its host, or the best tracer of dust? And the answer may not be that mass is the best, but mass does a really good job of taking out the majority of the signal. And so you can see this for the Pantheon 2018 analysis. It's 0 because it's already been taken out. And here it's important to characterize that when you're doing these kinds of tests, that you look at the differences between the second and third rungs of the distance ladder, and we see the differences are at the 20% level. We've mitigated this even further in Pantheon Plus, but really they don't change H0 at anything remotely close to the size of the tension at 6 or so. We can also test this another way. We can do what we're calling a 4-rung distance ladder. Now, why would you do a 4-rung distance ladder? Well, if you're concerned about the properties of the host galaxies in the second rung of the distance ladder. For example, as Radek had mentioned earlier, well, you can get a different sample of host galaxies in the second rung of the distance ladder. That's what's being shown here in this plot. The Cepheid hosts are here. The surface brightness fluctuation hosts are here. And so without going to the supernovae first, what we've done here is transferred the calibration to surface brightness fluctuation galaxies. We've added another rung, but really what this has done is it's allowed us to test a different sample of host galaxies and also by proxy a different sample of supernova properties. And again, you get an even higher value for H0. And then lastly, I'll just highlight very briefly that you can throw out the supernovae entirely. You can just do a 2-rung distance ladder. This is work by Darcy Kenworthy. And yes, this constraint is dominated by systematics and probably won't get better than 2.5 kilometers per second because you're dominated by the whole reason that we do a 3-rung distance ladder, peculiar velocity modeling uncertainties. But also there's the question of how you've selected the sample of Cepheids, which you don't have to worry about when you're doing a 3-rung distance ladder. But when you're doing a 2-rung distance ladder, you have to worry about the redshifts of the Cepheids and whether or not you've selected a redshift limited sample or a distance limited sample, which contributes to the uncertainty. But again, even throwing out the supernovae entirely, you get a high value of H0. So this sort of begs the question of going forwards, how could one change the local value of H0 in our analysis? And in the past, there's been a number of analyses that have raised some good ideas, many of which we've taken into account, if not all, in our analysis. And we seek to continually improve our analysis and add more variance motivated by the community. And I would sort of argue that these ideas fall in 3 main categories. The first sort of golden tier, I'll call it, is the motivated and empirical ideas. Those are the ones that have some idea based in either physics or based in specifically how the data is collected. And there is some model or hypothesis for why there would be a difference caused. And then something that we can actually test. So motivated and empirical. In the sort of second tier, which is something that we should be paying attention to, is, well, maybe you don't have a hypothesis or a motivation, but you can still look. You can still look for differences across the distance ladder. And we should take those into account too, but you have to be careful. Now, if you look in enough places without a hypothesis, you might find these 2 or 3 sigma effects. And then lastly, the tier that I won't even get into today is, the not motivated and not empirical. Really, the only evidence that you have for your idea, or lack of an idea, just is the movement of the value of H0. That's the only evidence. So those kind of, it's not really even testable. Okay, so now there was an example I can give of a sort of a golden tier idea that came out in 2015 and was updated with the updated Pantheon result sort of in 2018 by Michael Rigaud, which has suggested, and we've seen some figures on this earlier, that the stellar population age or the local specific star formation rate, which traces that, is physically tied to the intrinsic properties, namely stretch, which is then also propagated into the corrected standardized brightness, which is being shown here. So I'll note this is an external data set that is not representative necessarily of the full data set that we have in Pantheon Plus, but nonetheless, it's something that we should take into account. And we have in SHOES, we ensure that, again, the host properties are consistent across rungs. And that the supernovae don't live in different environments necessarily than in the second rung versus the third rung. And there's no reason to expect that they would, given the fact that all the second rung supernovae are now selected from the Pantheon Plus sample, which is a universal sample from redshift 0 to 2, not making any kind of additional selection function. And so we would argue this isn't really an issue for our 2022 analysis. And then I'll just remind you that we've cross-checked this essentially with the 4-rung distance ladder. When you go to the surface brightness fluctuation hosts, you're getting a different star formation rate, stellar population age. You're getting different stretch values of the supernovae, as I showed. So really, this has been cross-checked sort of two ways already at this point. Now, we heard a little bit about this earlier, but there's been some thoughts about, well, maybe this supernova color luminosity relation is different in the second and third rungs of the distance ladder. And so, well, I'll show you, this is sort of, we've seen this by Adam, but I'll just sort of re-highlight it in a bit more detail. The slopes are consistent between the second and third rungs of the distance ladder. Radek said that maybe 3 supernovae have changed since 2018. That's not surprising to me. There have been numerous updates, but they are not specifically changed. The whole analysis from end to end has been updated and improved, and we've added more samples. So this is not surprising. These data points are sort of representing the full combined sample data set. And really what the suggestion is that you need a delta beta between the two of about 1 to explain the difference in H naught, or so Radek says, I think. But what we find is that it's not inconsistent with each other. They're all selected from the same sample, and this sort of checks out. But let me take this a step further. Even if the delta betas were different, let's consider the method that Radek uses to move H naught, which is to change the mu values according to the delta beta times some reference color. And the reference color in the analysis is essentially the close to 0, which gives you the high value of H naught that I believe Radek would agree with. But it's when you use the reference color that's much more negative that you would potentially get a lower value of H naught. But the key thing I'd like to point out here is that if you change your reference color, you have to redo the entire analysis entirely from scratch. So this value, this arrow here, is plucked from actually one of my papers about the intrinsic supernova population color, which is this hierarchical, this property of the intrinsic population of supernova colors. But the standardization that we've done and the betas that we've obtained are from the observed colors. And this is by design. The observed colors are the measurables, or the okay, yes, I'm almost done. Are the observables that we have access to. And they are by design near 0 because a reference color, observed color, of a typical type Ia supernova would be about 0. And any deviation from that is what we believe to be a deviation due to dust. And that can be expressed in a linear relationship. If you take the reference color and move it away from 0, you're no longer going to have a linear relationship between the color and the luminosity. So I believe what Radek's doing will give you worse scatter if you do it from end to end, because you'll need to add an extra parameter to explain the intrinsic supernova color luminosity relation and the dust component. And really, to do it end to end, you need to refit beta and then calculate the difference in betas. Just plucking a reference color here is not an internally self-consistent way of rederiving H naught. So that being said, we have done our best to incorporate the ideas of the community, and that's what these 70 analysis variants here that Adam highlighted in the shoes analysis dive into. And on the supernova side, we've done that as well, where it really is hard to move H naught below about 72.5. You can see the differences on the supernova side and the reported uncertainty that we have on the supernova side when it comes to H naught, which we believe is a relatively conservative systematic uncertainty. So with that, I'll gladly leave it for questions and give you the information on how to access our data, which we are making all public. If there's something here that you have questions about, I encourage you to reach out. If there's something that's not here that you would like to use, I encourage you to reach out. We'll do our best to provide that for you. And with that, yes, happy to take questions.
Thank you, Dillon. Okay, yeah, I think you should come here. Okay. There.
Hi, thank you for the talk. I was wondering, so related to this talk in the previous one, so both theoretically and observationally, there is the idea that intrinsic color of Type Ia supernovae change. Actually, they're not all the same. So they might change with stretch. They might change with, for example, ejecta velocities or nebular velocities, so intrinsic properties. But also they seem to relate to the environment. So there's been it has been shown that some intrinsically redder objects are found in more metal-rich environments. So I see always that when there's cosmological analysis, you model always one intrinsic color, right, or one single color intrinsic color distribution. So I'm wondering if you tried other techniques, maybe taking into account that these observations and also theoretically you expect color variation for that one.
Yeah, I'll add. I added this one slide here. This is so. This is from my 2020 paper, where we look into it. It's not. I think it will answer your question, which is that our dust model with a single intrinsic parent population describes the data very well. That's the teal. And specifically, I want you to focus here. These are the residual, the scatter in the Hubble diagram. So the scatter in the Hubble diagram has a minimum. So the best, you can do your best standardization at around minus 0.08 or 0.09 in color. And that corresponds to the intrinsic color population, which is really what you're standardizing around. And if you have some one-sided dust population where the dust is kind of different in each galaxy, you can't really constrain that very well just using optical data, and you're really just introducing more and more scatter as you go redder. Now let's consider this two parent population approach, or two sort of key environments maybe that you're suggesting. I think that would be analogous, which is the pink. So the pink, you could maybe describe the distribution of supernova colors using two parent populations, but what you cannot describe is why we standardize the supernovae best over here at the bluer colors and not over here sort of at closer to color of 0, which would correspond to the mean of the two parent populations that you would need to describe the data set. So what I'm trying to explain here is that the scatter increases as you go redder, and the minimum scatter corresponds to the single intrinsic parent population, not to the middle of the two intrinsic populations.
Adam?
Yes.
Yeah, Adam, you can ask.
I'm sorry, can you hear me?
Yes.
Okay. Yeah, I was just going to add to what Dillon said in terms of the dust model. An even simpler story is there have been multiple papers showing that if instead of using these supernova observations in the optical, you use near infrared supernova observations where dust is minimal, you get the same answer for the Hubble constant. Also, if you replace supernovae with surface brightness fluctuations, you get the same results. So I don't see how you can do this with dust.
So I have a general question, are you satisfied with the general strategy of, standardizing supernova? There are lots of, data properties that we don't model and simply ignore, the distribution of light parameters, for example. I mean, here, for example, you show that, for the distribution of color.
Sorry, we can't hear. We heard like the first half of that question, but it's hard to hear.
I'm going to make the question very short. Would you envision some kind of, the motivation to do full forward modeling of the supernova data, where you will model all physically relevant parameters which are not directly available in observations, like exclusion, for example, color and so on. You can integrate this basically, if you have a full probabilistic model for forward modeling, you can integrate it with the selection constant, which is now done separately. Is there any discussion, to create such a tool?
There's a lot of, I think I heard your question. There is a lot of effort to do sort of a full forward modeling approach, but as you said, it's actually the selection function piece that is the most difficult to include in the forward modeling simultaneously with cosmology. And so there is effort going into that. Bahamas, Steve, many others that are doing this, but they haven't really done it on production real data. They've sort of been able to do it on toy models, but once you introduce real selection functions that are uncertain on real data, it sort of, it struggles. So yes, I hope that there's progress made, but it's sort of still it's not there yet.
Okay, and the last question. Can you show this plot with the different modulated and new model and the new from data?
Didn't hear. I'm sorry.
Yeah, please, can you?
I brought this Leandros. Can you please show again this plot with the data? So this is formulate new minus new model.
If someone heard that, can they maybe type it or repeat it? Because I'm struggling to hear that.
Can you show the plot with the difference between the two distance moduli, new minus new model, what the volumetric forensic bias induces some change? This one, definitely. Now, as we can see from this one, there is it's not consistent with a fixed constant distance modulus, and so in principle, this bias would show an evolution of the modulus due to this systematic. Now, if you don't correct for this, this would interfere with the cosmology. If we assume a fixed M for fitting the Pantheon plus data, instead of taking into account this effect, this could in principle interfere with the model best fit model parameters that you find when you fit cosmology. Now, you have shown, of course, that it doesn't affect WCDM because you put very large errors there. But I wonder if it would affect, for example, cosmographic expansion parameters like Q node or even H. Take into account this.
Is not hearing. So probably it's better if you talk.
Whoever is closest to the microphone maybe can summarize that question, because I can hear that person.
I've run out of time, so probably he will email. So let's thank Dillon again. Thank you very much.